All right, in this explainer, we're going to pull back the curtain on how a simple idea becomes a real, live app on your phone. We're diving into the secrets of software engineering.
You've been there, right? That light bulb moment. You've got this amazing idea for an app that could literally change everything. But then, that big question hits you. What's next? I mean, how do you take that spark and turn it into something real that people can actually use?
Because, let's be real, turning that idea into reality is, well, it's incredibly hard. If you just jump straight into coding without a solid plan, you're pretty much guaranteed to end up with a buggy, chaotic mess. It's so much more than just writing code. And this is where software engineering comes in to save the day. The official definition from the IEEE says it all. It's the professional discipline that brings order to all that potential chaos. The words to remember here are systematic, disciplined, and quantifiable. It's about building software the way an engineer builds a bridge, with a blueprint, with precision, and with a result you can actually count on. So why do we need such a strict discipline for this? Well, think about building a house. You wouldn't just show up with a pile of wood and start nailing boards together, would you? No way. You need a professional approach, because building anything complex, whether it's physical or digital, is just plain hard. And here are just a few of the reasons why. For starters, users often don't even know exactly what they want. And even if they do, things change. On top of that, technology is moving at lightning speed. When you're dealing with massive, complex apps, trying to map everything out perfectly from the start is almost impossible. You can see how this could get out of hand fast, right? To manage all that complexity, the very first thing you need is a building plan. In the software world, we call this a process model. This is your high-level strategy, the game plan you pick before anyone writes a single line of code. Now, this is where it gets really interesting. You've got two classic approaches here. On one hand, you have the waterfall model. It's super rigid, very linear. You do all the planning, then you do all the designing, and then you do all the coding, one step after the other. But then you have the incremental model, which is way more flexible. You build and deliver the app piece by piece. Think about the business impact here. Waterfall might be great for something with super fixed requirements like software for a medical device, but incremental, that's perfect for a startup that needs to get a product out fast and adapt based on what users are saying. So once you've got your plan, it's time to lay the foundation. For software, this means figuring out the requirements. This is the part where you define exactly what the software needs to do. It's just like deciding how many bedrooms and bathrooms you want in your house before the construction crew shows up. And these requirements come in two main flavors. You've got your functional requirements, that's what the app does, the features you see, like a search button or an add to cart function. Then you have the non-functional requirements. That's how well it does it. Things like speed, security, the quality stuff. And you absolutely need both to have a product that people will actually want to use. And getting those requirements right isn't just a guessing game. It's a whole detailed process. You start with a feasibility study, like, can we even build this thing? Is it technically possible? Financially viable? Then you gather all the info from the people who will use it, you analyze it, and you document everything in a formal document, usually called a Software Requirement Specification, or SRS. And then you check it all again to make sure you're actually building the right thing. This whole process is designed to prevent a disaster later on. Okay, the foundation is laid, the blueprints are approved. Now it's time for the actual construction. This is where we get into designing the software's architecture and, finally, writing the code. And this slide right here is pure gold. It shows two of the most important principles in software design. High cohesion means every part of your code does one specific thing and does it well, kind of like a perfectly organized toolbox. Low coupling means all the different parts are independent, like Lego bricks. You can swap one out or change it without making the whole thing fall apart. This is what separates clean, maintainable software from a tangled mess. And then comes the coding. This is the part everybody thinks of first, but look at how much planning and designing happened before we even got here. Coding isn't just hammering out text on a keyboard. It's a disciplined craft. It's about translating that beautiful design into instructions a computer can actually follow, all while keeping it clean and easy to understand for the next person who has to work on it. So, the house is built, but you wouldn't just move in without a full inspection, right? Of course not. It's the exact same with software. This next phase, testing, is absolutely critical to make sure everything works the way it's supposed to. And testing is all about answering two very different but equally important questions. Verification asks, are we building the software right? Does it match our blueprints? And then validation asks, are we building the right software? Does it actually solve the user's problem? You can build a flawless piece of software that nobody wants. You need to check both. Testing also happens in layers, building up from the smallest part to the whole shebang. You start with unit testing, testing one tiny piece, like a single light switch. Then you move to integration testing to see if the switch actually turns on the right light. After that comes system testing, where you check the whole house's electrical system. And finally, you have acceptance testing. That's the final walkthrough with the homeowner, where they give the thumbs up. So how did testers do their job? Well, they have two main strategies. With white box testing, they can see all the internal code. It's like an electrician who can look at all the wiring inside the walls. But with black box testing, they have no idea what the code looks like. They just test it from a user's perspective. I flip this switch, does the light turn on? Yes or no? So we built it. We've tested it. Now comes one of the toughest parts of the whole project, figuring out the final cost. This is like getting the final bill from the contractor and making sure it matches what you agreed to in the beginning. And I'm not going to lie, this is notoriously difficult to get right. Trying to accurately predict how much time, effort, and money a software project is going to take is a massive challenge. But for any business, it's absolutely essential for managing budgets and resources. To estimate the cost, you first have to estimate the size of the project. One way is to just count the lines of code, or LOC. It's simple, but it can be really misleading depending on the programming language. A much better way is to use something called function points. This measures the actual functionality the user gets, no matter how it was built. It's a much more modern and accurate way to size up a project. This quote from our source material just hits the nail on the head. It explains why all of this matters so much. Real projects are messy, they never follow a perfectly straight line. And if you use a rigid plan like waterfall, you might not have anything that actually works until the very end. That's a huge risk, and it's why having flexible plans and good estimation is so critical. So every single app you use, your banking app, your social media, your favorite game, it went on a journey just like this. It's a journey of disciplined engineering, not just a burst of creative coding. And that leaves us with one last question to think about. What do you think happens when a team decides to skip one of these crucial steps?